In the previous lecture, we have defined what is meant by Riemann integrability of a function. Now comes the next question, as we said in the last lecture, that are there enough functions which are Riemann integrable? That is, does there exist examples of a large class of functions which are Riemann integrable? Now, the so-called nice functions of calculus, that is continuous functions or differentiable functions, we want to know what they have to do with Riemann integrability. That is, are continuous functions Riemann integrable, and so on. Now, for that, we need a criteria by which we can check whether a function is Riemann integrable. As we said in the last lecture, something like Cauchy criteria of convergence of a sequence. We cannot always check convergence of a sequence by finding the limit. What we do is, we show that the sequence is Cauchy sequence. We are searching for a similar kind of criteria for Riemann integrability. Now first let us define RAB. What do we mean by that? This is the set of all functions defined on the closed interval AB which are Riemann integrable. So in mathematical symbols, we want to know how large RAB is. Now for that, the first theorem is a necessary sufficient criteria for Riemann integrability. So the theorem is this, that a function f belongs to RAB if and only if the following is true. If and only if given any epsilon bigger than 0, there exists a partition P of AB such that UPF minus LPF is less than epsilon. So the criteria is, given any epsilon bigger than 0, one can find a partition P such that corresponding to that partition P, if I look at UPF and LPF, then the difference between those two numbers is less than epsilon. We will see that it satisfies the criteria of being necessarily sufficient for Riemann integrability of a function. So for the proof of this, let us first assume that f is Riemann integrable, and then given any epsilon bigger than 0, I will find a partition P such that UPF minus LPF is less than epsilon. So let f belongs to RAB. Okay, and choose epsilon bigger than 0. Now for the first question is, how do I get hold of the partition P which is going to satisfy that criteria? How do I get hold of a partition P? Well, it is very simple. What I do is, since f is Riemann integrable, I know the lower Riemann sum and the upper Riemann sum both are same, because f is Riemann integrable. So we know that integral a bar to b f is same as integral a to b bar f. That is known to us. Now, what is the definition of this quantity a bar to b f? If you recall, this was defined as supremum over all partition P of the numbers LPFs, and a to b bar f was defined as infimum over P of all the UPFs. since epsilon is chosen, I will start with epsilon by 2, and I can say that integral a bar to b f minus epsilon by 2, that is, if I decrease the supremum a little bit, then there is some member of the set which is bigger than this decreased supremum. So this is then less than LPF, I call it LP2, for some P2 which is a partition of AB. Similarly, if I increase the infimum of the UPFs by epsilon by 2, then I know it is bigger than some UP2F for some partition P1, where P1, P2 are partitions. Well, this is just from the definition of supremum and infimum. So what have we done? I know that the lower Riemann sum is the supremum of the LPFs. So I decrease the lower Riemann sum by epsilon by 2. But since it's a supremum, then the supremum minus epsilon by 2 will be superseded by some LP1F. That is what I have written. Then I looked at the infimum of the UPFs and increased that by epsilon by 2. Then there is one UP1F which is less than that increased infimum. That is the thing I have done. Now I look at P, which is a partition of AB, and is a common refinement of P1 and P2. What does this mean? P1 is a subset of AB, so is P2. I take another subset of AB which is bigger than P1 and P2. So that is a refinement. And then I know the following thing, that UPF is less or equals to UP1F, and I also know that LPF is bigger than or equals to LP2F. This is the result which I have proved in the last lecture. Now what does this mean? I look at the quantity UPF minus LPF. This then is certainly less than or equals to UP1F minus LP2F. Okay. Now, from the previous relation, I know that UP1F, so I will write it again, UPF minus LPF is less than or equals to UP1F minus LP2F, which is further less than or equals to, let us look at the previous page. I know this relation, that UP2F is less than, so I will use that. This is less than or equals to A to B bar F plus epsilon by 2, then minus of A bar to B F minus epsilon by 2 from the previous relations, which then is equals to epsilon plus integral A to B bar F minus integral A bar to B F. Now notice that F is Riemann integrable. It means that the lower Riemann sum is same as the upper Riemann sum. That means this first quantity is same as the second quantity. That means the portion in the bracket is actually equals to 0. That means this is equals to epsilon by the fact that f belongs to RAB. But this is what we wanted to prove, because I found a partition P which is actually the refinement of P1 and P2, and that P satisfies that UPF minus LPF, this quantity, is less than or equals to epsilon. This is precisely what we wanted to prove. But now we have to look at the converse. So far what we have proved is that if f is Riemann integrable, then given epsilon bigger than 0, I can find a partition P such that UPF minus LPF is less than epsilon. Now what is the converse of this? I will assume that given epsilon bigger than 0, there exists a partition P which satisfies the given condition, and from that I need to show that f is Riemann integrable. Now if I want to show that f is Riemann integrable, the only way we can show it is by showing that the lower Riemann sum is same as the upper Riemann sum. Okay? So let's try that. Now what is the relation we have? Anyway, we have that LPF is always less than or equals to integral a bar to b fx dx. This is the lower Riemann sum, because we have defined the lower Riemann sum as supremum of all the LPFs. So this is true for all P. Similarly, I have UPF is bigger than or equals to integral a to b bar fx dx for all P, because the upper Riemann sum has been defined as infimum of all the UPFs. Well, this means what? It means that UPF is bigger than or equals to integral a to b bar fx dx, but the upper Riemann sum is always bigger than or equals to the lower Riemann sum. So this is bigger than or equals to integral a bar to b fx dx, which by definition is bigger than or equals to LPF. This is true for all partitions P. Now the given criteria tells me that given epsilon bigger than 0, there exists P such that UPF minus LPF is less than epsilon. Now from the previous inequality, what we get is that a to b bar fx dx minus a bar to b fx dx is less or equals to, so from the previous inequality now we get that the left hand side is less than or equals to UPF minus LPF. But I have chosen the partition P in such a way that UPF minus LPF is less than epsilon. That means that this difference between the upper Riemann sum and the lower Riemann sum is less than epsilon. But this upper Riemann sum and lower Riemann sum are two absolute constants. They don't depend on anything. Given the function f, that is a constant. The difference between those two numbers is less than epsilon for all epsilon. Means what? It means both the numbers are same. So this implies integral a to b bar f is same as integral a bar to b f. But this is precisely what is meant by f is Riemann integrable. So the result follows. So here what we have done, we have just used the fact that given any arbitrary epsilon bigger than 0, I can find a partition P such that UPF minus LPF is less than epsilon. And using that, I have shown that the difference between the upper Riemann sum and the lower Riemann sum is less than epsilon. That means upper Riemann sum has to be same as the lower Riemann sum, because epsilon I can make as small as I like. That means f is Riemann integrable. Now we are going to use this criteria to prove integrability of certain functions. So the first one is the most important one. This incidentally will prove that the class of Riemann integrable functions are quite large. The only property we are using about Riemann integrability of functions are bounded functions. Remember that. Time and again I am using the fact that f is bounded. It doesn't make sense to talk about Riemann integrability of a function which is not bounded. Okay? We are talking about integrability of bounded functions only, otherwise in the very definition the supremum and the infimum which we are using may not exist. Now the theorem says that if f is a continuous function on the closed interval AB, then f is Riemann integrable. So that I will explain by saying f belongs to RAB, the set of all Riemann integrable functions. So it proves that every continuous function is Riemann integrable. So how to prove this? We have to go by the necessary sufficient condition of Riemann integrability of a function. That is what we are going to use. That is the previous result. Okay? Remember, the previous result says that if I can somehow show that given any epsilon there is a partition P such that the difference between UPF and LPF is less than epsilon, then f is Riemann integrable. That is what I need to show here. So I start with an epsilon bigger than 0. Now my job is to find the correct partition for which the relation would be true. Here at this point I use uniform continuity of the function. This is a result which we proved in some previous lecture, that if I have a continuous function defined on some closed interval, then the function is actually uniformly continuous. The difference between the uniform continuity and continuity is as follows. Continuity says, continuity at a point x0 says that given epsilon there is a delta bigger than 0 such that certain things happen. Now the delta which exists because of the epsilon depends on the point x0. Uniform continuity means this choice of delta works for all x. It is independent of the x0. That is what I am going to use now. So by uniform continuity of f, there exists delta bigger than 0 such that for all xy in the closed interval AB, modulus of x minus y less than delta implies mod of fx minus fy is less than epsilon. This is the uniform continuity. Notice this delta does not depend on the points. Whatever xy you choose, if mod x minus y is less than delta, then modulus of fx minus fy is less than epsilon. Okay? Now what I do is choose a partition P of AB. Let us say P equals to the set with the following property, that delta xi, that is the length of the subintervals which appears because of the choice of the partition, this is less than delta for all I. That is, I am choosing a partition P of the interval AB such that the length of different distance of any two consecutive points in that partition is less than delta. That can be done. However small delta is, maybe I will be choosing large number of points so that this happens. I can look at the picture. This is A, this is B. I can choose very closely related points, but there will be only finitely many, such that the distance between any 2 points, between two consecutive points, is less than delta. Okay. Now once I do this, then the following things happen. I look at UPF minus LPF. Okay. So this then is equals to summation over I from 1 to n capital Mi times delta xi minus summation I from 1 to n little mi times delta xi, which then is same as summation I from 1 to n capital Mi minus little mi times delta xi. Now these delta xi's, I know they are less than epsilon. But what about this capital Mi minus little mi? This is where I am going to use the uniform continuity actually, because what is capital Mi? Capital Mi equals to supremum of fx, where x belongs to xi minus 1 xi, and little mi equals to infimum of all the fx such that x belongs to xi minus 1 xi. Okay. Now I know that modulus of fx minus fy, this quantity is less than epsilon if xy belongs to xi minus 1 xi, because the length of the interval xi minus 1 xi is less than delta, and hence by uniform continuity, if I take 2 points x and y from that interval, then modulus of fx minus fy is less than epsilon. Now the supremum of the function f and the infimum of the function f will be attained in the closed interval xi minus 1 xi, because f is continuous. So capital Mi minus little mi, I can certainly say is certainly mod of f alpha I minus f beta I, where alpha I and beta I are points in xi minus 1 xi. Okay. And hence this quantity is lesser equals to epsilon. So this means what? This then implies that UPF minus LPF, which is summation I from 1 to n Mi minus Mi times delta xi, is less or equals to epsilon times summation I from 1 to n delta xi. That is, Mi minus capital Mi minus little mi is dominated by epsilon for all I. So in the sum I am replacing those quantities by epsilon I am getting something bigger. But then I can sum it up to get epsilon times b minus a, because total length of the subintervals in the partition P is certainly equals to b minus a. Now b minus a is constant and epsilon is arbitrary, so it can be made arbitrarily small. This implies UPF minus LPF can be made less than epsilon. You know, this is the standard stuff. I mean, given epsilon, you start with, I will write it here, given epsilon bigger than 0, start with epsilon 1, which is defined as epsilon by b minus a, to get UPF minus LPF less or equals to epsilon 1 into b minus a, but epsilon 1 is epsilon by b minus a multiplied by b minus a, you get epsilon. That is it. So this shows that any damn continuous function defined on the closed interval AB is actually Riemann integrable, and see how easy it is by using the necessary sufficient criteria of Riemann integrability. That is precisely what I have done. Given epsilon bigger than 0, I have just shown that there exists a partition P such that UPF minus LPF is less than epsilon. But that is enough to show Riemann integrability of a function. Now the question is, can I give examples of a large class of functions which are not continuous but Riemann integrable? Well, that can also be done. Continuity is not necessary. So the next theorem proves that there are enough discontinuous functions also which are Riemann integrable. So the theorem says, if f from AB to R is a monotonic function, then f is again Riemann integrable. See, there is no question of continuity here. I can just choose any monotonic functions. It might be monotonically increasing, it might be monotonically decreasing, but then still it is Riemann integrable. So we will prove this assuming that f is monotonically increasing. The proof for monotonically decreasing function is analogous. So let's go to the proof of this. Suppose f is monotonically increasing. I want to again try to see whether I can prove the necessary sufficient criteria of Riemann integrability. That is, given epsilon bigger than 0, I will try to find a partition P such that UPF minus LPF is less than epsilon. So choose epsilon bigger than 0. Okay. Get n such that b minus a divided by n is less than epsilon. Okay. Choose a partition P now such that delta xi is less than b minus a by n for all I. In the partition, what you do is choose points in such a fashion that the difference between two consecutive points is always less than b minus a by n. That can be done. Now notice one more thing, that since f is monotonically increasing, capital Mi is actually equals to f of xi and little mi is f of xi minus 1. This is simply because f is monotonically increasing. At the right hand point, the value of the function is highest, and at the left hand point, the value of the function is lowest. Then I look at UPF minus LPF. And if I calculate this, I know what is going to come. It is summation I from 1 to n, mi minus mi times delta xi, which anyway is less or equals to, since each delta xi is less than b minus a by n, I can take it out of the sum, and what remains is I equals to 1 to n. I just write it in the fashion f xi minus fx I minus 1. Okay. Now if I sum them up, what I get is b minus a by n times, because of the cancellation, I get that this is b minus a by n times fb minus fa. So this is certainly less than epsilon times fb minus fa. Again, using the trick, because fb minus fa is constant and epsilon is arbitrarily small, I can make the quantity, this quantity can be made arbitrarily small. That is, I can always do by choosing epsilon smaller and smaller one. This is precisely what we have done in the last result also. So that shows that the function satisfies the necessary sufficient criteria of the Riemann integrability. As a result, f is Riemann integrable. So now we have seen that there are enough examples of functions which are Riemann integrable. Next we need some elementary properties of Riemann integration. So that I will put as a theorem. So first one is, if f belongs to RAB and C is a real number, then look at the new function CF, that is the scalar multiple of f, that also belongs to RAB. Not only that, integral a to b fx dx is same as integral a to b c fx dx. That means the scalar which I have multiplied with the function can be taken out of the integral. Second property is, if f and g both are Riemann integrable, that is, they belong to RAB, then the new function f plus g, that also belongs to RAB, and integral a to b f plus g x dx is same as integral a to b fx dx plus integral a to b gx dx. Third property is, if f and g both are Riemann integrable and fx is less or equals to gx for all x in AB, then their integrals also maintain the same relation, that is, integral a to b fx dx is less or equals to integral a to b gx dx. Fourth property, if f belongs to RAB and C is a point which lies between A and B, then f belongs to RAC. Well, here what I mean is, if I restrict f on the interval AC, then f belongs to RAC. That is what is meant by this. If I restrict f on CB, then also f belongs to RCB. That is what I mean. And integral a to b fx dx is equals to integral a to c fx dx plus integral c to b fx dx. Then the last property, the most fundamental one, that if f belongs to RAB, then the function mod f also belongs to RAB, and modulus of integral a to b fx dx is less or equals to integral a to b mod fx dx. We will see that this inequality has fantastic applications. Most of the important theorems will need this inequality. Now here most of the results we will not prove because they are very standard and follows in the standard way from the definition of the Riemann integration. You can try it out yourselves. So what I will do is, I will try to prove only 3 and 5 because that is what I need now. So I start with the proof of 3. What I do is, I define h equals to g minus f. F and g both are Riemann integrable. This then implies that h is Riemann integrable by 2. This is by 2. Okay. Now I look at, well, according to my notation, then it should be LPH. Well, I look at LPH, that is summation over I little mi times delta xi. Here little mi is the infimum of the function h over all the subintervals. Now since h is always a non-negative function, because f is lesser equals to g, implies g minus f is bigger than or equal to 0. So h is always bigger than or equals to 0. That means this mi is also bigger than or equals to 0. That means this is bigger than or equal to 0. This is true for all p. This then imply that the lower Riemann sum, that is a bar to b hx dx, which is supremum of all the LPFs, in this case LPH, that is bigger than or equal to 0. But then again by 2, this would imply that integral a to b hx dx, well, I had integral a bar to b hx dx, how can I write it as integral a to b hx dx? Well, by the previous property, since f and g are Riemann integrable, I know h is Riemann integrable. So the lower Riemann sum, upper Riemann sum are same, that is the Riemann integral. So integral a bar to b hx dx is same as integral a to b hx dx. That's why I could write this. This is bigger than or equal to 0. But then this would imply that integral a to b gx dx minus integral a to b fx dx, this is again by 2, is bigger than or equal to 0. But that means integral a to b fx dx is less or equals to integral a to b gx dx. This is the conclusion we wanted to prove. So this proves 3. Now I want to prove 5. So here the only trouble is to prove that if f is Riemann integrable, then so is mod f. Suppose I know this, then the result is actually obvious. That we will see very soon. So first I assume f is Riemann integrable. I have to prove that mod f is Riemann integrable. It follows very easily that if P is a partition then supremum of mod fx over any set, let us say S, minus infimum of mod fx over the same set S is certainly less than or equals to supremum of fx over S minus infimum of fx over S, right. It is because of the oscillatory nature of the function. F can take the positive value as well as the negative value, then the infimum will be negative, supremum will be positive, but for mod f both the quantities are positive. So the difference between the supremum and infimum of mod f is always less than or equals to the difference between the supremum and infimum of f. Now instead of S, I actually want to concentrate on xi minus 1 xi. So this then implies that supremum over the set xi minus 1 xi mod fx minus infimum over the same set xi minus 1 xi mod fx is less than or equals to supremum over the set xi minus 1 xi of fx minus infimum over xi minus 1 xi fx. What does this actually show? It shows that if I concentrate on mod f, then the corresponding capital Mi minus little mi is less than the corresponding quantity of f, right. So this then implies if Mi prime is equals to supremum of mod fx over the set xi minus 1 xi and correspondingly Mi prime, then Mi prime minus little mi prime is actually lesser equals to capital Mi minus little mi. This then implies that summation over I capital Mi prime minus little mi prime times delta xi is lesser equals to summation over I capital Mi minus little mi times delta xi, which in turn implies up mod f minus lp mod f upf minus lpf. Now since f is Riemann integrable, I know that given epsilon bigger than 0, there exists a partition P such that UPF minus LPF is less than epsilon. This, because of the previous inequality, then implies that UP mod f minus LP mod f is less than epsilon. But that means mod f is Riemann integrable because of our theorem, that this implies mod f belongs to RAB. So at least this much we have proved. But now we have to prove the inequality of the integrals. Well, that follows quite easily. We have anyway that minus mod fx is lesser equals to fx is lesser equals to mod fx. This is by definition of modulus. Then look at the theorem Now we want to use 3. By 3, then we have that minus integral a to b mod fx is less or equals to integral a to b, which is less or equals to but this precisely means that modulus of integral a to b fx dx is less or equals to integral a to b mod fx dx. By the definition of mod f, this is same as integral a to b modulus of fx dx, which is precisely what we wanted to prove. And now we are going to use these things for the most fundamental results of Riemann integration, that is the connection between Riemann integration and the differentiation of function. Now our first theorem concerning integration and differentiation of function is the first fundamental theorem of calculus. It says that suppose f belongs to RAB, I define gx as the given integral, then this integrated function g is a continuous function of f. Further, if I assume that f is continuous at a point, mind you, to start with f has just been assumed to be Riemann integrable, not continuous at all. If I further assume that f is continuous at a point x0, then the integrated function g turns out to be better. In fact, it is differentiable at x0 and the derivative of g at x0 is given by fx0. So let's come to the proof of this. Since f is continuous on the closed interval ab, well, I am just assuming f to be a bounded function, so certainly I can say that capital M is equals to supremum of mod f x in AB. That will be a finite quantity because f is a bounded function, so the supremum exists. Now I start with modulus of gx minus gy. If I just write it down, it is modulus integral a to x ft dt minus integral a to y ft dt. Using a previous result, this is same as modulus x to y ft dt. Then I use the last inequality which I have proved, then this quantity is less or equals to integral x to y mod ft dt, which then is less or equals to integral x to y m dt, which is nothing but m into mod x minus y. So it follows then that modulus of gx minus gy is less or equals to m times mod x minus y for all xy in the closed interval ab. What does this mean? This implies g is actually uniformly continuous, something more than continuous. This is the first part of the result. Now assume that f is continuous at x0. I want to show that g is differentiable at x0 and the derivative is f at x0. So by continuity, I can say that given epsilon bigger than 0, there exists delta bigger than 0, such that modulus of fx minus fx0 is less than epsilon if modulus of x minus x0 is less than delta. So I choose some x in AB such that modulus of x minus x naught is less than delta. And then look at the corresponding modulus like this, gx minus gx naught divided by x minus x naught minus fx naught. The idea here is to show that this modulus is less than epsilon, because then it would prove that if x converges to x naught, then the quotient gx minus gx naught by x minus x naught converges to fx naught. But that would precisely mean that g prime at x naught is fx naught. Well, now I just write down the definitions. This would imply then modulus of 1 by x minus x naught times integral x naught to x ft dt minus f of x naught. That is okay. This just follows from definition of g. But now I use a trick. I write it as 1 by x minus x naught times x naught to x ft dt. No change here. The next quantity I write as 1 by x minus x naught times integral x naught to x f x naught dt. Notice that in the integrand there is no function of t, fx naught is constant. That means it will come out of the integral. F of x naught will come out of the integral and the integral becomes just x minus x naught. But in the denominator there is an x minus x naught, they will cancel each other. So the end result is fx naught, which I already had in my case. Now I write this as modulus of 1 by x minus x naught times integral x naught to x ft minus fx naught of dt modulus. And then I use the inequality which I have already proved. It is 1 by modulus x minus x naught times integral x naught to x modulus of ft minus fx naught dt. Notice that t varies now in between x naught and x. So by continuity criteria, modulus of ft minus fx naught is less than epsilon for all such t. So what I get is that this is less than epsilon by modulus of x minus x naught times modulus of x minus x naught. They cancel each other to produce epsilon. So this would then imply that g prime at x naught is equals to fx naught. So that is the first fundamental theorem of calculus, that you look at the function g, which is now a function of x, which appears as the upper limit of the integral. The integrand is f. Wherever little f is continuous, at those points the function g is differentiable and the derivative of g is f. If I don't have continuity, I just have Riemann integrability of the function little f, then it turns out that the function g is just a continuous function. In fact, it is an uniformly continuous function. Now we come to the second fundamental theorem of calculus. It says that integration of a derivative is the original function. So the precise statement is this, that suppose f belongs to Rab, if there exists a differentiable function g such that g prime x equals to fx for all x in AB, then integral a to b fx dx is gb minus ga. Another way of writing would be that integral a to b g prime x dx equals to gb minus ga. So to prove this, we proceed as follows. Given epsilon bigger than 0, choose a partition P of AB such that UPF minus LPF is less than epsilon. I can do that because f is known to be Riemann integrable. Now I look at the quantity g of xi minus gxi minus 1. Since g is known to be differentiable, I can apply mean value theorem that would tell me that this is g prime ci for some ci times delta xi, which is same as f of ci times delta xi. Well, then it follows that summation I equals to 1 to n f of ci times delta xi, that is equals to summation over I gxi minus gxi minus 1, which will certainly turn out to be gb minus ga. Okay. Now, I also know that LPF is less than or equals to this summation I from 1 to n fci times delta xi and less or equal to UPF, because UPF comes from the maximums of f and LPF comes from the minimum, but Ci is an arbitrary point, so it lies in between. So this is okay. Also, I know that LPF, since f is Riemann integrable, is less or equals to integral a to b fx dx, which is less or equals to UPF. Because integral a to b fx dx can be thought of as the upper Riemann sum, which is the infimum of the UPFs, so it is certainly less or equals to UPF. It can also be thought of as the lower Riemann sum, which is the supremum of the LPFs, so it is certainly bigger than or equals to LPF. This would then imply that modulus of summation I from 1 to n fci delta xi minus integral a to b fx dx is less than epsilon. But this then implies from the previous inequality that modulus of gb minus ga, because I have already proved using mean value theorem that summation I from 1 to n fci delta xi is same as gb minus ga. So this minus integral a to b fx dx is less than epsilon for any epsilon bigger than 0. But this would then imply, since epsilon is arbitrary, that a to b fx dx is equals to gb minus ga. So this is the end of the proof of the second fundamental theorem of calculus, and this is the result most of the time we have used to find integrals of certain functions. If we can view it as derivative of something, then calculating the integral is becoming very easy. So second fundamental theorem of calculus is the most important one to evaluate the integrals. So this is more or less all about Riemann integrations, which we wanted to prove, the most fundamentals one. Now we will go to higher dimensions outside real line to Rn to do differentiation and integrations. All of those results will be the analogues of the results which we have proved so far.